We're now going to start delving a little deeper into some of the concepts that underlie the completable futures framework in Java. And in order to make sense of completable futures and the asynchronous paradigm it espouses, it promotes, we really have to start by understanding a bit more about synchronous computing. So this particular part of the lesson is going to talk about what synchronous computing means in order to motivate the Java completable futures mechanisms. And we'll talk about the pros and cons of synchrony. So first, what does it mean to be synchronous? Well, most method calls in typical Java programs historically have been largely asynchronous. For example, if you have a hash map or an array list, and you do something like a get or an add or a remove or a contains, that blocks the caller while the computation takes place, and then you get a result back. Similar things happen in Java streams with aggregate operations. So if you think about when we did operation calls to do things like looking up words in the works of Shakespeare or looking up phrases or whatever, the caller would make a call, it would block the caller, the callee would do its thing and return a result. So the way to think about this in synchronous programming, the callee, which is the thing that's been called, borrows the thread of control of the caller, the thing that makes the call, until the computation is done. That's synchronous programming. And we'll see that there's some pros and cons to that particular approach, of course. The basic idea here is these are request-response interactions. You can read more about request-response here, but basically you make a call, you block the caller, callee does the thing, returns the result, you go on and do the next thing. These are two-way synchronous calls. Well, there's some good things about this model. One of them is it's relatively intuitive to program and relatively intuitive to debug. And the reason, of course, for that is we've done this most of the time we've programmed. It would be a rare person who started out with asynchronous programming. Maybe if you started with JavaScript or something like that, and promises and so on in JavaScript, you might have learned asynchronous programming first, but it's kind of unlikely. And it's intuitive because it maps onto these two-way request-response method patterns. Another nice thing about synchronous communication is the local caller state is retained on the runtime stack of activation records such that when the callee returns to the caller, the state is automatically restored to what it was before. What the heck does that mean? Well, let's take a look at an example. So here's an example where, and you can see this example if you take a look at this code. This particular example is going to download the contents at a URL and return a byte array of that content. And you can see here what we do is we go ahead and we allocate a new byte array, we create a new output stream for byte array, then we use a try with resources block to open a connection to that URL, and then we read the contents of the connection and write them to the output stream. And everything that I've highlighted, buff, OS, IS, and bytes and so on, those are all local objects whose state is automatically restored when method calls return. So when we call read, that pushes another record on the stack of activation records, a call record. And when it comes back, IS and bytes and OS and buff and so on, they all have exactly the same values they did when the call was made. You do not have to explicitly save and restore the state. But of course, not everything is rainbows and unicorns. As I like to say, there are some downsides to synchrony as well. One of the most obvious ones, which is really the driving force here for this course, is if you use synchronous communication, it may be difficult to leverage all the parallelism that's available in multi-core systems. So you may have lots and lots of cores, but if you do purely synchronous communication, your threads may spend a lot of time blocked, which is bad. Blocking is bad for several reasons. It typically incurs overhead, synchronization overhead, context switching overhead, data movement, memory management overhead. When you block, you can often incur those overheads. And if you use an asynchronous approach, you don't incur those overheads. This is a funny little meme I always get a kick of. This is parallelism or concurrency in theory versus in practice. So you would like to have everybody all working in an embarrassingly parallel fashion, not having to share anything, not having any contention or corruption. And in practice, you start spawning threads and it all goes down the drain really quickly. Another challenge is selecting the right number of threads. For example, let's say we have a parallel stream, not unlike your programming assignment 2, where you want to download some images from a remote server. How many threads should you have in your thread pool to do this effectively, given that these are blocking calls? Well, it's a hard choice. So you either may want to optimize for efficiency and have a lot of threads, but then you'll end up using too many resources, or you might want to optimize for resources, but then things won't be as efficient. So if you have a large number of threads in the pool, that can be efficient, but you'll waste resources. If you have a small number of threads, you might be efficiently resource-wise, but you'll end up with having bad performance. So that's a tough choice to make. And it's particularly tricky for I/O-bound programs. We've talked about this before. Remember the distinction we talked about last time in class about I/O-bound operations versus CPU-bound operations, and their difference in performance, and you have to typically have different numbers of threads, and there are different consequences of doing things. So it becomes hard to tune with purely synchronous programming styles. If you're programming in the parallel streams world, you may need to change the size of the common fork join pool. So you may need to make it grow or shrink. One way to do that is by setting a system property, but that is difficult because you don't know what the size should be, and also it has to be done before anything runs at all involving the common fork join pool. Another way to do it is to use the managed blocker mechanism, which is a good solution if you understand how it works. It's not that hard, but it's a little bit crufty if you're not well-tuned at writing, well-versed in writing wrappers and things that encapsulate complexity. And a managed blocker can only be used with the common fork join pool. You can't use it with other kinds of pools. So that's the end of a quick overview of the pros and cons of Synchrony. Now, just to make some things clear, Synchrony is not inherently evil. It has pros and cons. And what your job as a student and ultimately as a professional, if you pursue this line of work, is to know what approaches to apply and what context to apply them in. So you have to understand the approaches, and you have to know the consequences of applying them, both good and bad.